All right, here's a video on, I did a video on the compound miters for handrails, which is actually kind of a compound oblique miter where they fish mouth into each other. And pretty rare. I've only had that happen very rarely. And I did those rails for years and years. So this is typically what you'd find as a compound miter on a column. Pretty rare also. Uh, it's in the corner of a, this was monolithic concrete, right? The bottom half, and then the basement, I guess you'd call it, and then this column went in that corner of the monolithic concrete, and then plumb here, and it was, you know, it had to be exactly true and plumb because it was on these are great windows, micro windows, big large windows, and they wanted to minimize this column in the corner. So, and it had rebar, you know, stuff tied onto it. But I'm going to go into the geometry of how I figured this out, and I don't remember the numbers many years ago, almost 20 years ago. So I'm going to say it was 20 and 15. And so what you do is you're looking at the 20, and it's 16 feet tall from the corner. It didn't really matter what the height was back here, right? We're looking at the height in the corner, so the angle doesn't change. So, and a 16 is kind of an arbitrary number. I know it was about 15 or 16 feet. So you go vertically 16 feet, and then you put the 20 degrees on it, and then you calculate this width here. So, I don't know, the trigonometry is pretty simple, or the rise run calculator is pretty simple. And then you project that down, so you get this, that 5.824 projected down. So it's projected down to here, right, between the here, H, K, enter. What the hell? .824. I didn't do any checking on these. You know, I didn't do any. Normally you do this and you check, make sure everything's exactly right. And then, but I didn't do any real checking. So, and then over here is the same thing. It's coming in the horizontal direction on the 2D page here. So you calculate that 4.287, and then you end up with that here, right? Alright, so those are matched up. Now you've got the triangle here. You can calculate this diagonal, just this squared plus this squared to get the square root of that, and that'll get you your 7.231. I'm thinking, right? Square root. .824 caret 2 plus 4.287 caret 2 close parenthesis, and you should end up with that 7.2317. There you go. And then, right, and then so now you have this direction. You're looking at a plan view of the true profile of that piece, right? This is a diagonal, this is plumb, and then you need to project that down at 90 degrees to here out I think right there, right? 90 degrees. So all these projections are coming out at 90 degrees. And this is grayed out a little bit because you actually have to, if you want the true plan view of that, you actually have to come back around from the other direction. So you start out here, and you take these core points. This thicker line is the part that you'd actually see. So this line, and this line you can see. And then this one, these two would be hidden, looking at the, you get over here looking at this, right? This is an actual piece. It's rotated relative, you know, the same orientation as that piece right there. So this gives you where they intersect the top corner. Let's see, top corner. Yeah, this is the one that you can see right here. The most closest one. Let's see. Maybe highlight that dark. Let's see, what am I doing there? So this is the one that's the closest. Maybe I'm not looking at. This is the top, right? And then this is the side view. Yeah, so the top, yeah, so this line here is the highest point looking down, and then that looking at the side is the inside line right there. And then you have, so what you end up with this, that 7.231 is the width down here from the outside corner to the inside corner. All right, you end up with that 7.231, and that means you can calculate with the 16-foot high. So the top piece is 12 feet. Just like I said, I'm just picking out numbers out of my hat to say that top piece there is 12, and this is 16 feet in elevation, not in the diagonal. Then you can calculate the diagonal right there. All right, and then that means now you have the rise and the run of this piece. You can calculate this angle here, or this angle here, Alt MA. I thought I did that somewhere. Yeah, right here, 24.32. It's the angle of the dihedral angle of this piece while it's laying on its side, right? But then you can calculate the miter here. So some saws will have the cut off of 90, which means you'd set it to 77.84, or if you have a typical miter saw, it'll be showing the cut off of square, which would be 12.16. So you can cut those like that. You can tip it right in the saw at 36.36 degrees. That's calculatable. That's calculable from here, because this piece is sort of like, I forget what they call it, but it's the lid of a box that's going away from you, perpendicular to this line here, right? Perpendicular to all those lines is going away. So you could picture that as let's see, picture it as being on the table. This is the bottom of the table, bottom of the saw, right? That you'd be measuring the angle from, right? So I'd have like a wedge or a block or a template piece that would give you that angle, right? And then, so that's the rotation angle, and it's going to be the same over here, even though the angles up top are different. It's all working with one dihedral angle and then the one rotation angle. And so there's your angle there. There's your height, 12 feet from the corner to the top, and you know, maybe it's even, you'd want to equalize that if you want. You could let's say, and then you got your height, your length, you got your angle, and then this is just showing how you project that out if you needed the individual angles. Right here we know that's 6 inches. It was a 6-inch tube, I think, and then so this is 6 from here to here, right? But visually it's much less, but the tangent, this line is actually true to scale. F4, so it's going to be 3/4 of an inch and 6 inches. So you go tools, calculator, A10 0.064 divided by 6, close parenthesis, and that'll give us put A10 0.064. I'm thinking that's like 7 degrees or something, divided by 6, close parenthesis, enter. Not 0.6. I have a hard time believing that. That's arc tangent. Oh, point zero. Oh, yeah, because it's 0.06 and it's in feet. So our tangent, 0.06 divided by 0.5, because it's 0.5 feet, 0.064 feet. Let's see, 4. All right, so yeah, there's 7.294 degrees, 7.294. If we look over here, pretty good guess, huh? 7 degrees, LMA, F4. There you go, 7.29, 7.28. I'm not sure why there's a little difference in that, but it should be exactly the same, right? 0.064. So there must be some math error in there. 0.064. If we took that out a little bit more, precision to 50639, 810. Should end up with something a little more accurate. 7.283, 7.283. Yeah, so there was just a little rounding error. Anyways, that's why that works, is because you're looking at the tangent in the plan view here. The rise for that 6-inch run, that is a true dimension. Then you just got to put the 6 there, and or 6 inches to 3/4 of an inch. And let's see, so that's how they get those angles if you're not sure. And then here's the angle, we calculated that. And it's the same thing here. You just look at this from here. Here's the top highest point on that rotated piece right here, right there. And then from there to there, to a dimension right there to there. We're looking at about 1.5 inches, right? So it's going to be 1.5 inches, probably 25 degrees or something. Doesn't look that much though, does it? So from there to there, Alt MA JS 15 degrees. So let's see, 15 degrees. That rise is F4. Looks bigger to me. 1.5 inches and 6. That's bigger than 15 degrees if I had to guess. Nope, 15 degrees. So let's do that. Let's just double check. Tools, calculator, A10. Uh, 0.134 divided by 0.5. Enter, and we get 15 degrees. So that's how that works. And that's pretty much it. You get your length, your angles, your deal here, and then when you put them together, you don't put them together just with your miter. The accuracy that might be kind of low compared, if you're running this whole thing. So you got to run this line all the way down to 16, and then measure over, get your square, and then get a nice big square, or calculate the 16, 7.231, and then calculate this length and describe that arc, get a point right there, and then lock it in, and then double check it. I would double check it with a large miter, large protractor, digital protractor or something. Just check and recheck. But anyways, that's how I did it, and many years ago, and I thought I'd add that because it came up. I don't know how many times I did those, maybe 10 times in my whole career, but thought I'd share it with you, and hope that helps in your career. Thanks for watching.